Hi guys, this is a video of the day one from the exponentials unit. First we are looking at graphing an exponential function. When we do look at these functions, they're in the form of y equals a times b raised to the x, where a, which is your coefficient, cannot be 0, and b, which is your base, cannot be 1. This is a nonlinear function that changes by equal factors over equal intervals. All that means is that we have this function here. This number here is your base. And this here is your exponent. Now, if we were to put into our calculator y equals 2 to the x, you would see this exponential function here. If we were to look at our table, we would see x values increasing by 1, and we would see the corresponding y values. Now, as you can see, there's a pattern with our y values. Going from any y value to the next value, we're really just multiplying by a constant of 2. And that pattern holds true. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. So we can look at the equation of y equals 2 to the x, and our base, again, of 2, in this case is known as a growth factor. And this just means that the y values are being multiplied. By 2 for every 1 increase in the x value. You can see here the x-axis. Now it looks like this function is going to touch the x-axis. It's actually not. This x-axis is known as an asymptote in this function because the function gets infinitely close to it, never actually crosses it. And that's all an asymptote is. It's an invisible boundary that the function gets infinitely close to without actually crossing it or touching it. So that's what this next part says. The x-axis is an asymptote. And a line that the curve approaches, gets very close to, but never actually touches. That's the asymptote. So in here, it says, what is the y-intercept? The y-intercept is where your function crosses the y-axis, as you already know. If I were to look at my graph, crosses the y-axis right here. That's at 0, 1. As far as an x-intercept, it looks like it's, like I said, going to cross here. It's actually not. It's going to get infinitely close without crossing the x-axis. So our x-intercept here, there is none. And if I were to look at the equation of that asymptote, in this case, it is a horizontal boundary. We draw those with a dashed line. Kind of hard to see because this axis is so thick, but I could label that as y equals 0. And that's going to shift around with our transformations. It's going to shift up and down if we add or subtract a constant, but I'll talk about that more in a moment. Next, we have the domain and range. The domain of exponential functions is never going to change because it's going to go left forever and it's going to go right forever. So we could say negative infinity to positive infinity, or we could just say all real numbers for our domain. For the range, it depends on where the asymptote is. Here, since it is at a height of 0, we're going to say our lowest most height gets infinitely close to 0. To show that, I use the parentheses. To show non-inclusive, that's my lowest most height. My highest most height, this would go up infinitely. Could even have an arrow on each end. And that would go up to infinity. So in that one, because this base here was larger than 1, it's known as growth factor. That's going to increase. You're going to see in the next problem, we have exponential decay. So instead of the function going up very quickly, it's actually going to start high and go down very quickly if this base here is a fractional value between 0 and 1. So in order to graph this, I can just use my graphing calculator. And I'm just entering in the function y equals, I'll just go through and type this again, parentheses, 1 division 2. You can type it exactly as you see it, raised to the x plus 1. That x plus 1 is actually going to be our left-right shift. Whenever that constant is being added or subtracted in the exponent, that's our left-right shift. When the constant is added at the end or out front, that's your up-down shift, and you'll see that more in a moment. Plus 3. So then I can look at the graph just by hitting zoom 6, and I see that exponential function shifted up. So I can plot my points from the table. First, I'm going to record those points. So I need to scroll up. So it starts with an x value of -3. We have -3 corresponds to 7. -2 corresponds to 5. -1 to 4, so on. I'm just going to record all these points just as I see them. And you can see that these numbers are getting very, very close to a value of 3 without actually reaching it. Now, if I were actually to scroll down in the table, it would appear as though we reach a value of 3, but that's just because our calculators can't display that value with any more decimals without it just looking like a 3. But it never actually will touch or cross that value. Now, when I do graph this, I'm going to actually start out with the asymptote. I can see that plus 3 here means that asymptote that was previously at a height of 0 is now going to be at a height of 3. So I go 1, 2, 3. It's always going to be a horizontal asymptote. Again, I'm just drawing it as a dashed line because it's that invisible boundary. And we have y equals 3. You always want to label those. So now when I graph this, it's going to get very close to that line without crossing it. So back 3 up 7, back 2 up 5, back 1 up 4, and so on. And you're going to see it gets very, very close. You don't have to plot all those small decimals. They're just going to get really, really close to that asymptote without actually crossing it. When you do connect those points, just be careful not to cross that asymptote. We're going to get really, really close to it, but we're not going to cross it. And that is the equation of that is the function showing decay this time. You can see it's going from high to low. So as far as our domain, again, that's always going to be all real numbers for exponentials. As far as the range, our lowest most height is at that asymptote of 3. Our highest most height, it goes up to infinity. If this was like a -3, this would be -3 to infinity. If this was a 7, it would be 7 to infinity. The y-intercept, that's where it crosses the y-axis. Your y-intercept is always going to correspond to where x value is 0. So we can state the coordinates 0 and 3.5. The x-intercept, it doesn't cross it, so we have none. And what is the equation of that asymptote? We already said it's at y equals 3. And that'll always be seen in that up-down shift. And 1/2 is now called our decay factor, as opposed to our growth factor. I know it's a decay factor because that base is a value between 0 and 1. So So we'll talk about that more on the next page. So if we are given the exponential function y equals b to the x, if your b value is greater than 1, then you're going to see that growth pattern where it gets higher and higher and higher. If your b value is a fractional value between 0 and 1, then we can say that we have exponential decay. It starts up high and gets small very quickly. So some properties to know for our exponents or our exponential function. We always write it out as y equals a times b raised to the x. A is your initial value, also known as the y-intercept. So that is very important when we look at the y-intercept. We're looking for where we have an x value of 0. So x will always equal 0 when we're looking at that y-intercept. So our y-intercept here, that's our a value. And then b, which is your base, is called the growth or decay factor, depending on that value of b, but it'll always be positive. If it's negative, we no longer have an exponential function. The domain will always be all real numbers. And an exponential function will always approach but never cross a y value. This is the asymptote of the graph. And the range is always dependent on that asymptote. So the asymptote will always be y equals some number. That number is based on our up-down shift. So a review of our transformations. When we see that constant being added or subtracted, that's that up-down shift I keep referring to. If we're adding a constant, we're going up c units. If we're subtracting a constant, we're going down c units. If you're adding the constant and it's in with your exponent, that's our left-right shift. And remember, we always take the opposite of what you would think. So x plus c, we would think we're shifting to the right. We're actually going to be shifting to the left c units. Same with this, x minus some constant. We would think we're going left, so we are in fact going right c units. If this leading coefficient here is greater than 1, we say it's vertically stretched. By a. And again, that's if that leading coefficient is a number greater than 1. If it's a fractional number between 0 and 1, we say it's vertically compressed. By a. And last, we have our two reflections. If your leading term is a negative out in front of that coefficient, we would have a reflection. So if this a value here is negative, we're going to have a reflection over the x-axis. You can write those words out or do the proper notation, which is a lowercase r subscript x-axis. And then if you see a negative in the exponent, see that's negated. We have another reflection. However, this time it is over the y-axis. So now we can look at some equations. We can state the transformations that occurred, and then we're going to establish whether this equation represents growth or decay without just by simply putting it in your calculator, although you could. So first, this function here that I'm looking at, if I look at that base, we are transforming the parent function y equals 2 to the x. So as if that were our original function, we want to state what's happening to this and to get here. So first, I see the negative out front. I'm going to say that there is a reflection over the x-axis. I see a fractional coefficient. that leading coefficient is between 0 and 1. So I'm going to say it is vertically compressed by A. Next, this 2, like I said, that 2 isn't doing anything in the form of a transformation. That was just my parent function. And then this x plus 1 in the exponent, that's going to be our left-right shift. Plus 1, we'd think right 1, so we know we're going left 1. And then last, this being growth or decay. Well, if we look at our b value, which is our base, we would say here our b value is greater than 1. So we are going to say that this is a growth function. As you can see in our next example, we have a base less than 1, more specifically between 0 and 1, so that's going to be your decay. But first, looking at the parent function, to see the parent function, just look at the base. What are we raising something to? We have 1/4 raised to the x. That's just our original function that is being transformed. That 3 out front, that's our vertical stretch. That's the only thing happening to this basic function. We have this was vertically stretched by 3. Oops, and I just realized in my last one I should have said that was vertically compressed by. You can actually input that value, that coefficient, 1/2. I would not put negative 1/2. That negative correspond to the reflection. You just input that number. So same here, we say vertically stretched by 3. There's no up-down shift. There's no left-right shift. If I were to see a left-right shift, you would see that as a constant being added or subtracted to the exponent. An up-down shift would be a constant added just outside. And then, like I said a moment ago, this fractional base means that we have exponential decay. And then the last one. So here we would be working off the parent function of y equals 5/3 raised to the x. So we can see we have a left-right shift and we have an up-down shift. I'm going to do my left-right shift first. We always say that up-down to the last part. So -3, I would think we would go left 3. We know we're going to go right 3. Right 3, and then the 7 added to the function tells us we would shift each point up 7. Now you want to be careful here. Some students will say this is decay because it's a fraction. It's only decay if this is a fractional value between 0 and 1. This is a number that's greater than 1. Since that base is greater than 1, we actually have exponential growth. On the next page, you're given some information and you're being asked to write the equation of an exponential function. So remember, we're just going back to our y equals a times b raised to the x, where a, again, is our y-intercept. And our y-intercept will be always in the form of 0, comma, and then that y value. And then as far as the b, that's our base, which is our growth or decay factor. So if we look at our table here, first thing I notice is that we have an x value of 0 here, which means this here is my y-intercept. That's my a value. As far as my b value, my growth or decay factor, it's what's being multiplied each time. So to get from 3 to 12, or 12 to 48, or 48 to 192, and so on, I can see that pattern is that we are multiplying by 4, which means 4 is my B value. That's that growth factor. So again, we're doing y equals a times b raised to the x. In this problem, our a value is 3. Our b value is 4. So now we can write our final equation, 3 times 4 raised to the x. We often put that base in parentheses. Even if there's no parentheses seen to be there, that base is the only thing that's being raised to that exponent. So you would never multiply the 3 and the 4. Those can't be multiplied because 4 is being raised to the x, 3 is not being raised to the x. So that would be your final function. In letter B, we have a similar scenario where we're given coordinates. So we just have x and y values. Now I do need to establish what my y-intercept is, so I'm going to start with an x value of 0. Now in this we have x values of 2 and 3. I just want to count by ones up to 2 and 3. I'm going to state those corresponding y values. 2 corresponds with 20 and 3 corresponds with 4. So now I'm noticing the pattern that to get from 4 to 20 when I'm going up appears though that I'm multiplying by 5. So I'm going to multiply 20 by 5. We get 100, multiply 100 by 5. We get 500. So we can see our A value here, which is our y-intercept. That would be 500. Now you have to be careful for B. It's what are we multiplying by as our x values increase by 1. So what we're multiplying by to get from 100 to 20, well, a lot of students will say we're dividing by 5, which isn't wrong, but you want to show us what are we multiplying by each time. Dividing by 5 is the same as saying multiplying by the reciprocal. The reciprocal of 5 is 1/5. Take a fifth of 100, we get 20. Take a fifth of 20, we get 4, and so on. So that is our B value. So I'm ready to write the function. Y equals a times b raised to the x. So we have 500 times our b value, which is 1/5, raised to the x. Now, if you had a hard time coming up with what am I multiplying by to get from one value to another, you could also write out an equation. You can pick any 2 consecutive y values and say, what am I multiplying 100 by to get to 20? You can make an equation that just says 100 multiplied by some unknown value will give me 20. That x, that unknown value, will be our b. So just solve for x like you normally would, divide by 100, divide by 100, and you would see that b value is 1/5. So you can always use that if it's not so obvious. Next, we are going to look at applications with percent increase and decrease. This is an equation that you saw back from Algebra 1. This formula does have a plus and minus in it. It's not going to have both. It's going to be one or the other. If you have an amount that is going up or being increased, we're going to use plus. If you have a value depreciating, losing value, going down, we would say we're going to use subtraction if the amount is decreased. So this A value on the outside, you can think of that after amount, A and A, which actually means your final amount. Our P is our initial amount. That will always be seen in your coefficient. And your R is your rate. Now your rate is always written as a decimal, but sometimes they'll ask us the percent of change. if they ask us the percent of change, we just take our rate and we multiply by 100, and that will equal the percent. And then your t represents time. So in these given equations, we are being asked to identify the initial amount. Remember, that's going to be your p-value. The percent of change. So the percent of change is your rate times 100. And determine if the rate is a rate of growth or a rate of decay. So first I'll start with the easiest one, our initial amount. That's going to be our leading coefficient, which is 65. To find your rate, it's always the difference of this number and 1. So if I think of what the difference is between $1.25 and $1, I would say I have a difference of 25 cents. So it's always the difference of that number that's in the parentheses and 1. But again, it did ask for the percent of change. So I'm multiplying that by 100 to get 25%. Last, to establish if this is growth or decay, just like we did previously, it's just looking at, is this number greater than 1 or is it less than 1? Since that value is greater than 1, we have a growth function. So for the next one, we have a p-value of 9.5. Our rate is going to be the difference of this and 1. So if you think of in terms of money, what's the difference between $1.92? Well, that would be 8 cents. I would write 8 cents as 0.08, not 0.8, because that would be 80 cents. And if I convert that to a percent, multiply by 100, really just moving your decimal over twice. And that would be 8%. Because this number, our base, is less than 1, this would be showing decay. And last, our initial value is 17. Our rate, think of this as 0.25. So what's the difference between a quarter and a dollar? Well, that would be 75 cents. That 0.75, we're just going to change that to a percentage, multiply by 100, and we get 75%. Because this number is less than 1, that would again be decay. So then last, we finish with one application problem. It says the population in Buffalo in 2014 was 245,000 people and tends to be depreciating, which means it's going down, by a 2.74% per year. So this is our rate, this time written as a percent. So to get from percent to decimal, that's where you divide by 100 or move that decimal 2 places to the left. Any little open divot there just gets a 0. So 0.0274 would be our rate. This 245,000 was our initial amount. That was our starting population. So this says rate and exponential model that represented the population in Buffalo T years after year 2014. So 2014 was our initial year. I'm just going to start with my general formula without plugging anything in. A equals P times 1. Again, we said this was depreciating, going down, so I'm going to use subtraction. With my rate raised to the time. Now I can plug in. I don't know the final population, but I do know that initial population was 245,000 times 1 minus that rate, 0.0274, raised to the t. And again, t is the number of years after 2014. So if we were looking at year 2015, t would be 1. If we were looking at year 2020, t would be 6. It would just be the difference between 2014 and that year we're looking at. I can clean this up a little bit. 245,000, I'm going to keep that as is for now. And if I just take the difference of these two numbers, I can put that right in my calculator. I get 0.9726 raised to the t. Now we can use that equation that we just derived to find out how many people will live in Buffalo in 2022. We are rounding to the nearest 100 people. That's not hundredths, but it's hundreds. So if we were looking at a population of in 2022, I'd have to say, well, what's my t-value going to be? How many years after 2014 is 2022? We can easily do that by just taking the difference in those years, subtracting those out, and we get our time in this scenario would be 8 years because 2022 is 8 years past 2014. So now when we plug into that equation that we just created, everything's going to stay the same, but we're going to plug in our t-value of 8. So we still have 245,000 times 0.9726 raised to the 8th power. When I enter that into my calculator, I'm going to enter it in just as I see it. 245,000, just do your parentheses, 0.9726, end parentheses raised to the 8th power. Before you hit enter, just double check that you've entered everything incorrectly. It's so easy to mistype a number, and we have our resulting value. Now I'm going to write out a good portion of that decimal and then round in the next step. So we have 196,173.43, so on. I didn't even have to go that far in my decimal because I'm rounding to the nearest 100 people. So the nearest hundreds, well, this is ones, this is tens, this is hundreds. So that 1 is up for possible rounding. I look over to the right, that 7 tells me to round that 1 up to a 2. So our population in Buffalo, according to this model, would be 196,200 people. And that's it. If you have any questions, you can come see me or your math teacher, and we can help you out with that.